Okay, so I think we're live, and I haven't actually participated in contests for a while, so let's just do that. In operation, actually, I'm not gonna bother. I'm just gonna do this. So this is just alright, prefix sum. I kind of forgot to do 2D prefix sum. Wait, how the heck do I do prefix? How do I do 2D prefix sum? So it's like I want okay, for it's equals to JM. Actually, no, I don't even need, I got my math wrong. I don't even need this. Grid plus equal grid ij. So p1 plus 1, j plus 1 is equal to something like this. I have no idea if this is right. 4, 6. 4, 6 seems right to me. Belongs to letter Y. The diagonal starting at top left and ending at the center cell. Okay, so we have literally a letter Y, all values. This is actually pretty interesting. So this will be a little bit annoying. So of course you want to go diagonal. Okay. So So this is a lot harder, but it's okay. So we'll do a BFS. Actually, I'll in Q. So we have res plus plus. So if right, so it's odd. So then we have it and supergrid size. Wait, this is actually really easy. So guess I just run solve. Okay. I actually don't need this ing. We just do in this odd. So that would just be odd would just be wait, what? All values of the cells not belong to y are equal. The values that cells belong to are different. Okay. Okay, so the structure is fixed. So that makes it really easy. So then all I have to do is so if it's like J is equal to okay, actually it's not y. Yx plus equals Think about this. Is this actually correct? So I plus 1. So if we have this, so if it's 0, it should be correct. Diagonal. Okay. Yeah, okay. Okay. If greater count, yeah, so this is actually a completely different problem. Maybe I should solve this first. If last time was greater than, okay. Yeah, I think it might be a good idea to solve this first. Okay, so if and it to, so then answer the insert. Okay, 231 5348. Okay, so we're looking kind of solid. How the frick does someone do this in 9 minutes? Wait, that's so easy. Oh Lord, oh no, oh no. There's exactly a data structure for this. What are the contest rules? Okay, so yeah, okay. I'm trying to solve it without that data structure. It's called ordered set in C++. It's extremely overpowered. Um, you can basically sort it. You can process it in some order. I think you can merge sort this. Well, okay, screw it. So it's yeah. So it's okay because this is pretty common. Python has their own sorted list, and I should have included this in my template. God damn it! So you do this, right? So you do this. Okay. And then you do this. And then, so I'm gonna put this in my template for future reference, but what the fuck is with this spacing? Okay, so order strictly smaller. So, oh my, ordered set int. Okay, so we still want to keep track of our answer A, B, and so then we just basically do what we did in the first problem. Okay, so we just do insert number 0. I think this needs to be a pair. we actually need to make this negative. I feel so bad. So if order by key, order of key, negative. Okay, so oh shoot. Seriously? Okay, so I so if CA is bigger than CB, else if CA is less than CB. So else if I mean technically like what? Oh, in the first operation, then the second operation. Oh my goodness, what? Why? This is literally so bad. Um, less or equal. So bad. 5, 3, 1, 2, 14. Okay, so that's the entire contest. So I'm just a little bit. Oh, sub 30. Let's go. This contest was basically free, so I'll go over my solutions and yeah. So by the way, it's not cheating because like in competitive websites, you use this. So something you have to know is, so if it's within your toolbox, you're justified to use it. Anyways, the first problem, so yeah, just kind of do what it says, and then you start from the third element to the end. You just check the last element, and then just combine them together. So the way I did it was this, which actually is really handy one-liner. So yeah, that's it. So this one, I think, is, I don't know, all these problems are boring. But anyways, what you're supposed to do is, because the main problem you will face is when you go and see like the sum of each sub-matrices, you don't want to literally count the sum over again and again and again. So what you can do is you can do a 2D prefix sum, and yeah, so you do a 2D prefix sum. You say, okay, from the top left corner to the current tile, what is the total sum? And you can, just reuse a prefix sum to figure that out. So this is a linear time. But yeah, 2D prefix sums. And the way I did it is I keep track of a separate variable for the prefix sum of the current row. So I don't have to do any shenanigans with, like, I don't know, it's kind of hard to explain. But this is the way I went about implementing the prefix sum. There might be other standard ways, but the goal is to be able to compute it and use it. So this one, I think, is actually interesting at the start, but then when you think about it, it becomes really boring. So because one thing you have to realize is the structure for the letter Y is fixed. So because it's not changing, we don't have to do any like paths or anything like that. So we just go through the entire grid. And the way I did it was I counted. So for example, this not Y means the number of changes I need to make on the tiles that are not on the letter Y to X. So basically, not Y of 0 means how many tiles that are not on the letter Y I have to change to get everything to 0. So yeah, just kind of compute this information. So I do it for 0, 1, 2. And yeah, this is just checking if it's on the diagonal and if it's on the straight line, the bottom part of the letter Y. Otherwise, you just add it. And I do the same thing, but specifically for the tiles on the letter Y. It's the exact same idea. So then I say here, so I want to make the tiles on the letter Y equal to I. So this is how many changes I need to make to do that. And for J, that would just be for everything that's not on letter Y. So I make sure J is not equal to I because of this requirement that values of cells belong to Y are different from cells not belong to Y. So here you just kind of try out your answers and pick the best one. Since you only have 3 distinct routes to work with, you can just do this brute force. But otherwise, you pre-compute this information so you can just query it pretty fast in this part of the solution. Now here, you can do a ordered set. An ordered set is a data structure. Imagine a normal set, but it has two more methods. One, it tells you the kth item, like from the beginning of the set. So if for normal ordered set, it would be like the kth smallest item. And then you have order of key, which is what I used here. It tells you how many elements are strictly less than this current one. So here you see I used a pair of ints. You might be asking, why do I do that? Because ordered set is like a set, which means it doesn't normally support duplicated elements. So I need this second number to kind of distinguish each duplicate. So I just have an ID. Every single time I put something in a set, I just increase the ID. So that way everything will be counted as their each own individual element. So since this set is telling us how many things are strictly less, we can transform this to how many things in array 1 that are less than negative of the current number. So if you think about it, if you want to make the ordered set count this, the bigger the number, and if you negate it, the smaller it will be because it will be a bigger negative, if you will. So then I follow this weird rule, and yeah. And then, in addition to keeping track of the actual arrays, I just have this order set to help me count. Now, if you don't know this, what I think you can do is, now this is where I have to think a little bit. My first instinct was merge sort. Yeah, merge sort will probably work because it allows you to count this. It allows you to count this for both arrays. But, never really worked with merge sort. But I think that is a solution. Another solution you can use is like a Finwick tree. All you need to do is you need to set up coordinate compression, and then you can basically query the Finwick tree for how many things that meets this condition. And then you can do the same thing with segment tree. Python has their sorted list. But yeah, I think merge sort will be the most optimal because you don't really have to do the coordinate compression. You just process it in order. If you learn how merge sort works, which again I've never really worked with, but I kind of intuitively understand how I can make it work. The actual implementation details I still have to figure out. But yeah, that's the entire contest, and it was a pretty boring contest. And see you guys.